In a He-Ni laser, the active medium is a mixture of helium, He, and neon, Ni, at a few torr pressure. Neon atoms provide the light-emitting transition, usually 632.8 nanometers, 3s sub 2 to 2p sub 4 in Paschen's notation. Helium atoms do not emit the laser light, but act as an energy transfer partner. Helium has a first excited state around 19.8 electron volts, while neon's relevant upper laser level lies at about 18.7 electron volts. When an electron in the discharge collides with a He atom, it can raise He to its excited state. A subsequent collision between an excited He atom and a ground state Ni atom transfers the energy to Ni, promoting Ni to its upper laser level. The upper laser level of Ni is metastable. It cannot decay to the ground state by a fast electric dipole transition. Its lifetime is on the order of 10 to 100 nanoseconds, long enough for photons to stimulate the transition. The lower laser level of the 632.8 nanometer transition is a much faster decaying state, approximately 1 nanosecond, so atoms quickly leave it, keeping its population low. Because the upper level lives longer and is continuously fed by He to Ni energy transfer, while the lower level empties quickly, a situation where N sub U greater than N sub L, more atoms in the upper level than the lower, is achieved. This is the population inversion needed for laser action. Analogy: think of a two-story building, upper level, with a fast elevator, lower level. He atoms act like a conveyor belt that brings people energy to the upper floor, while people on the lower floor quickly leave through a fast slide, keeping the lower floor less crowded. Section 2: Electrical discharge pumping mechanism and gas pressure effects. The helium-neon laser is pumped by a low-current DC or RF electrical discharge across the gas tube. Discharge, a high voltage, approximately 1 to 2 kilovolts, is applied between electrodes at the ends of the tube, creating a glow discharge. Free electrons are accelerated, gaining kinetic energy, and collide with helium atoms, exciting them. These excited helium atoms then transfer energy to neon as described above. Current density: typical discharge currents are a few milliamps for a 10-centimeter tube. The current density J equals I over A determines the electron density, which directly influences the pumping rate R sub P, number of excitations per unit volume per second. Pressure dependence: the optimal total pressure is about 0.5 to 1 torr. At very low pressure, collisions become rare, weak pumping. At very high pressure, the mean free path shortens, electrons lose energy in many small collisions and cannot reach the excitation energy of helium. Also, collisional quenching of the metastable neon levels becomes significant, raising the threshold. Mean free path: lambda equals K sub B times T divided by the square root of 2 times pi times D squared times P, where D is the molecular diameter, P is pressure. For 1 torr in room temperature, lambda is approximately 1 millimeter, suitable for a uniform discharge. Practical example: in a fluorescent lamp, the same principle is used, but the gas pressure is higher and the discharge is stronger, producing broadband light instead of a narrow laser line. Optical resonator design: mirror curvature, cavity length, G-parameter stability condition. A He-Ni laser typically uses a linear resonator formed by 2 mirrors, separated by a distance L. Mirror curvature: 1 mirror is often flat, radius R1 equals infinity, and the other is concave with radius R2, for example 50 centimeters. The curvature determines the mode size inside the cavity. G-parameters: for each mirror Gi equals 1 minus L divided by Ri. The resonator is stable when 0 less than or equal to G1 times G2 less than or equal to 1. For a flat concave cavity, G1 equals 1 and G2 equals 1 minus L divided by R2. Stability requires 0 less than or equal to 1 minus L divided by R2 less than or equal to 1, which implies 0 less than or equal to L less than or equal to R2. Cavity length: typical lengths are 10 to 30 centimeters, well within the stability range for R2 equals 0.5 to 1 meter. The longitudinal mode spacing, free spectral range, is delta nu equals C divided by 2L for L equals 20 centimeters, delta nu approximately 750 megahertz. Beam waist: for a flat concave resonator. The waist W0 at the flat mirror is given by W0 equals square root of lambda divided by pi times the square root of L times open parenthesis R2 minus L close parenthesis divided by R2, where lambda equals 632.8 nanometers. With L equals 20 centimeters, R2 equals 50 centimeters, W0 approximately 0.6 millimeters. Analogy: think of the resonator as a hallway with mirrors at both ends. The curvature of the far mirror acts like a gently curved wall that keeps a marching band, the light wave, focused as it walks back and forth. 4. Longitudinal and transverse mode analysis TEM sub MN, Gaussian, beam parameters and beam divergence. Longitudinal modes. Along the cavity axis, standing waves satisfy 2L equals Q lambda, where Q is an integer mode order. The frequencies are nu sub Q equals Q times C divided by 2L. Adjacent longitudinal modes are spaced by the free spectral range delta nu equals C divided by 2L for helium neon. Many longitudinal modes fall within the gain bandwidth approximately 1.5 GHz, typically 2 to 3 modes. Transverse modes TEM sub MN. The transverse field distribution follows the Hermite-Gaussian solutions. E sub mn of xyz equals E0 times W0 over W of z times h sub m of square root 2, x over W of z times h sub n of square root 2, y over W of z times exponential of negative x squared plus y squared over W squared of z times exponential of ikz minus I psi sub m n of z. Here h sub m are Hermite polynomials. W of z is the beam radius, and psi sub m n of z equals open bracket m plus n plus 1 close bracket arctan of z over z sub r is the Gaussian phase. Fundamental mode TEM sub 0, 0. When m equals 0 and n equals 0, the field is a pure Gaussian. It has the smallest divergence and best beam quality. Beam divergence. For Gaussian beam far field half-angle divergence theta approximately lambda over pi W0. With W0 equals 0.6 millimeters and lambda equals 632.8 nanometers, theta approximately 0.34 milliradians, approximately 0.02 degrees. Spot size at output coupler. Using Gaussian propagation, W of L equals W0 times the square root of 1 plus L over Z sub R squared, where Rayleigh range Z sub R equals pi W0 squared over lambda. For the numbers above, Z sub R approximately 1.8 meters, so W of L approximately W0, the beam hardly expands over a 20 centimeter cavity. Real-world picture. The TEM sub 0, 0 mode is like a perfectly shaped water jet from a faucet, while higher-order modes look like splashing patterns with multiple lobes. Small signal gain: the gain per unit length for the transition is G equals sigma EM open parenthesis and upper minus n lower close parenthesis, where sigma EM is the stimulated emission cross-section, approximately 3 times 10 to the minus 23 square meters for helium neon at 632.8 nanometers, and n upper. N lower are upper and lower level populations. Round-trip loss: includes mirror transmission, scattering, absorption, and output coupling. If the two mirrors have reflectivities R1, R2, and internal loss per pass alpha, the round-trip intensity factor is L equals R1 times R2 times e to the minus 2 alpha LC, where LC is cavity length. Threshold condition: lasing starts when the round-trip gain equals the round-trip loss. E to the 2G sub TH LC equals 1 divided by open parenthesis R1 times R2 e to the minus 2 alpha LC close parenthesis, which simplifies to G sub TH equals open parenthesis 1 over 2 LC close parenthesis times natural log of open parenthesis 1 over R1 times R2 close parenthesis plus alpha. Example calculation: for a 20 centimeters cavity, R1 equals 0.99 highly reflective, R2 equals 0.95 output coupler 5% transmission, and internal loss alpha equals 0.01 per meter. G sub TH equals 1 divided by 0.4 times natural log of 1 over open parenthesis 0.99 times 0.95 close parenthesis plus 0.01, approximately 2.5 per meter. Threshold pump power: the pump rate per unit volume needed to sustain n upper minus n lower that yields G sub TH is P sub TH equals H nu V G sub TH divided by sigma EM eta, where V is the active volume. Eta is the efficiency of energy transfer from helium to neon, approximately 0.3. Using V equals pi open parenthesis 0.5 centimeters close parenthesis squared times 20 centimeters equals 1.6 cubic centimeters, and nu equals C over lambda, we obtain a few milliwatts of electrical power as the threshold, consistent with typical helium neon tubes. Analogy: the threshold condition is like pushing a swing. You must supply enough periodic pushes gained to overcome friction loss for the swing to keep moving. Let N sub U and N sub L be the upper and lower level populations per unit volume. The basic rate equations are dN sub U over dt equals R sub P minus N sub U over tau sub U minus B sub ul rho of nu times N sub U minus N sub L. dN sub L over dt equals N sub U over tau sub U minus N sub L over tau sub L plus B sub ul rho of nu times N sub U minus N sub L. R sub P equals pump rate excitations per second per cubic meter from helium to neon collisions. Tau sub U and tau sub L equal the lifetimes of the upper and lower levels, tau sub U approximately 30 nanoseconds, tau sub L approximately 1 nanosecond. B sub ul equals the Einstein B coefficient related to the stimulated emission cross-section by sigma sub m equals lambda squared divided by 8 pi n squared tau sub U. Rho of nu equals photon energy density inside the cavity. In steady state, dN sub U over dt equals 0, and dN sub L over dt equals 0, and assuming n sub L much less than n sub U good inversion, we solve for n sub U. N sub U equals R sub P divided by 1 over tau sub U plus B sub ul rho. Photon density is linked to intracavity power P sub cav by rho equals P sub cav divided by C a sub mode, where a sub mode equals pi W sub 0 squared is the mode area. The output power through the output coupler with transmission T is P sub out equals T times P sub cav. Combining the above gives the useful expression. P sub out equals Th nu V R sub P divided by 1 plus tau sub U over tau sub L plus P sub out over P sub sat, where P sub sat equals H nu a sub mode divided by sigma sub m tau sub U is the saturation power approximately a few milliwatts. For pump rates far above threshold, the denominator approaches 1 and P sub out grows linearly with R sub P. Practical point in a typical helium neon tube R sub P corresponds to an electrical discharge of approximately 2 milliamps, giving an output of 0.5 to 1 milliwatt in the TEM00 mode. Wavelength the transition 3s2 goes to 2p4 of neon emits at lambda equals 632.8 nanometers. This value is set by the energy difference delta E equals hc divided by lambda. Precise wavelength is often measured with a Fabry, Perot interferometer, or a wavemeter. Natural line width determined by the upper level lifetime tau sub U, the full width at half maximum, FWHM. In frequency is delta nu natural equals 1 divided by 2 pi tau sub U for tau sub U equals 30 nanoseconds. Delta nu natural approximately 5.3 megahertz. Doppler broadening thermal motion of neon atoms, temperature approximately 300 Kelvin, causes a Gaussian broadening. Delta nu d equals nu sub 0 divided by c times the square root of 2k sub b times t times natural log 2 divided by m neon atomic mass m equals 20 atomic mass units, so delta nu d approximately 1.2 gigahertz. This dominates the gain profile. The laser selects a narrow slice about tens of megahertz within this envelope via the cavity. Laser line width the actual line width of a helium neon laser is much narrower than the Doppler width, typically 1 to 5 megahertz for a free-running device, limited by cavity pulling and acoustic noise. The Shallow-Townsend formula gives an estimate. Delta nu SD equals h nu times delta nu cavity divided by 4 pi p out times 1 over 1 plus alpha squared. Delta nu cavity is the cavity decay rate, approximately 1 megahertz, and alpha is the line width enhancement factor, approximately 0 for gas lasers. For P out equals 1 milliwatt, delta nu SD approximately 2 kilohertz, but technical noise raises it to a few megahertz. Coherence length L sub C equals C divided by pi delta nu. With delta nu equals 2 megahertz, L sub C approximately 48 meters. This long coherence enables interferometric applications such as holography. Analogy Doppler broadening is like the spread of colors you see when cars with headlights move past you at different speeds. The light gets slightly shifted in frequency depending on motion. Output coupling 1 mirror, usually the high reflectivity side, has reflectivity R sub H approximately 0.99. The output coupler has R sub O approximately 0.95. The fraction of intracavity power extracted each round trip is the transmission T equals 1 minus R sub O, approximately 5%. The coupling efficiency, eta sub out, is the ratio of output power to total generated power inside the cavity. Eta sub out equals T divided by open parenthesis T plus L sub int close parenthesis, where L sub int equals 1 minus R sub H R sub O e to the minus 2 alpha L sub C is the internal loss. With L sub int equals 0.02, eta sub out approximately 0.71, 71%. Output power using the steady-state expression from section 6 and inserting typical numbers, R sub P equals 2 times 10 to the 22 per cubic meter per second, V equals 1.6 times 10 to the minus 6 cubic meter, tau sub U equals 30 nanoseconds, T equals 0.05, yields P sub out approximately 0.8 milliwatt. Beam quality factor M squared measures how close the beam is to an ideal Gaussian. For a pure TEM00 He M squared approximately 1.0 to 1.2. Higher order transverse modes increase M squared proportionally to M squared, equals 2M plus 1 for the dominant mode index. Experimentally, M squared is obtained by measuring waist size at 2 positions and applying M squared equals pi W sub 0 theta divided by lambda, with W sub 0 equals 0.6 millimeter, and theta equals 0.34 milliradian, M squared approximately 1.0. Real-world link: the low M squared makes He lasers popular for alignment work and interferometry, because the beam stays tight over long distances. Derive the threshold gain condition for a linear resonator. Write round trip intensity factor G equals e to the power of 2GL, and loss factor L equals R1 times R2e to the minus 2 alpha L set G equal to 1 over L, which gives threshold gain G sub TH equals 1 over 2L times the natural logarithm of 1 divided by R1 times R2 plus alpha. Calculate longitudinal mode spacing for a 30 centimeter cavity. Delta nu equals C divided by 2L, which is 3 times 10 to the 8 meters per second divided by 0.6 meters, giving 5 times 10 to the 8 hertz, or 500 megahertz. Find the beam waist of a flat concave cavity with length 15 centimeters and radius 40 centimeters. Use W0 equals the square root of lambda over pi times the square root of L times R minus L, divided by R substituting lambda equals 632.8 nanometers, gives W0 approximately 0.45 millimeters. Given reflectivity of the high reflector 0.99, output coupler reflectivity 0.96, internal loss 0.01 per meter, cavity length 20 centimeters, compute output coupling efficiency. Transmission T equals 1 minus RO, which is 0.04. Internal loss L sub int equals 1 minus RH times RO times e to the minus 2 alpha L, which evaluates to 1 minus 0.99 times 0.96 times e to the minus 0.004, giving approximately 0.030. Output coupling efficiency eta out equals T divided by T plus L sub int, approximately 0.04 divided by 0.07, about 0.57 or 57%. Estimate the coherence length for a laser with line width 3 MHz. Coherence length L sub C equals C divided by pi times delta nu, which is 3 times 10 to the 8 meters per second divided by pi times 3 times 10 to the 6, giving approximately 31.8 meters. Compute threshold pump power using threshold gain G sub TH equals 2.5 per meter, and emission cross-section sigma sub M equals 3 times 10 to the minus 23 square meters. Required population inversion N upper minus N lower equals G sub TH divided by sigma sub M, which is 8.3 times 10 to the 22 per cubic meter. Pump power threshold P sub TH equals Planck's constant times optical frequency times the volume times the inversion divided by efficiency. Using a volume of 1.6 times 10 to the minus 6 cubic meters and efficiency approximately 0.3 gives a threshold power of about 2 milliwatts electrical. Explain why increasing the output coupler transmission beyond 10% reduces output power. A higher transmission increases extraction, but also increases the loss term in the denominator of the threshold condition, which raises the required threshold gain G sub TH. The cavity then cannot achieve sufficient inversion, and the net output power decreases. Determine the beam quality factor m squared from a measured waist of 0.5 millimeters and divergence of 0.4 milliradians. M squared equals pi times W0 times theta divided by lambda, which evaluates to pi times 5 times 10 to the minus 4 meters times 4 times 10 to the minus 4 radians divided by 632.8 times 10 to the minus 9 meters, approximately 1.0.